In this video, we're going to talk about the change of base formulas for logarithms. Perhaps you already know that if y is equal to the log base a of b, then y is equal to log b over log a. Now you might be curious, why is that? Well, it's actually rather simple. First, imagine you have the expression y equals log base a of b. Okay? Well, obviously then the equivalent exponential expression would be a to the y is equal to b. Okay, just by rearranging that logarithmic expression. Now, what we're going to do next is we're going to take the logarithm on both sides. If a to the y equals b, then the log of a to the y equals the log of b. But then we can take this y and move it in front and say that y log a is equal to log b. And then finally, we can simply divide both sides by the log of a, and we have the formula that we just described a moment ago. Y is equal to log of b over log of a. Okay? And so this is what's described on these slides here. Take the logarithm of both sides, use the power rule of logarithms to bring the y down in front, and get the result that we indicated. Now, this rule is useful because not every calculator evaluates logarithms of different bases. Many calculators only have a log button and, of course, a ln button. As I mentioned in an earlier video, ln refers to the natural logarithm, or log base e. So suppose that we wanted to evaluate the log base 2 of 8. Well, we know that the log base 2 of 8 is equal to 3 because 2 to the 3 is equal to 8. But suppose we didn't know that. If we didn't, then we could simply follow these steps. The log base 2 of 8 is equal to the log of 8 over the log of 2. The log of 8 is roughly 0.903. The log of 2 is roughly 0.301. When you divide the exact value by the exact value, you get 3. So we can use just about any scientific calculator to evaluate complicated logarithms because scientific calculators generally have log buttons. Now, look to see if your calculator has a ln button, ln. It probably does. In math, ln, ln, stands for logarithm naturel, which is French for natural logarithm. So what is that? Just like the common logarithm is log base 10, the natural logarithm is log base e. You might be wondering, what the heck is e? In mathematics, e is a constant. It's approximately equal to 2.71828182885. Now, it's similar to pi in the sense that it's an irrational number, goes on infinitely with no discernible pattern. And when we take calculus, that's when we really learn the importance of it. But putting that aside for a second, if you want to use the ln button instead of the log button when you do this change of base rule that we just learned, you can use it so long as you use it in both the numerator and denominator. So for instance, we know 2 cubed equals 8, so log base 2 of 8 equals 3. But if you forgot that and needed your calculator to figure it out, and your calculator did not evaluate log at different bases, then you're fine. You could do what we just explained a moment ago and say that the log base 2 of 8 is log 8 over log 2, or you could say the log base 2 of 8 is ln 8 over ln 2. The ln of 8 is roughly 2.079, and the ln of 2 is roughly 0.693. When you divide the actual exact values, you get the same answer of 3. So the change of base rule works regardless of which base of logarithm we use in the numerator and denominator, so long as we use the same base in both numerator and denominator. So the best way of expressing the change of base formula is this. The log base b of a is equal to the log base c of a over the log base c of b. Okay, so that's a pretty useful formula that we're going to be able to use in questions coming up. Now, we could take this even further. the log base b of a is, as we just said, log base c of a over log base c of b. But we could also have said that the log base b of a is log base d of a over log base d of b. So obviously then the log base c of a over log base c of b must be equal to the log base d of a over log base d of b, which leads us to the second change of base rule. The log base c of a over the log base c of b will equal the log base d of a over the log base d of b, so long as the usual assumptions about bases of logarithms and arguments of logarithms are followed. And this formula is also sometimes useful. So let's look at all the rules that we've learned so far, including rules from previous videos and slideshows. The number one rule to remember is that when 3 is equal to log base 2 of 8, 3 is called the value of the logarithm, 2 is the base of the logarithm, 8 is the argument of the logarithm. And here are the rules. The argument of a logarithm must be positive. 8 is positive. The base of a logarithm must be positive. That 2 is positive. The value of a logarithm can be any real number. We can have 0 here, we can have negative values, fractional values, positive values, it's fine. Now, if you do not see a base on the logarithm, it means that we're using base 10. So if you did not see that number 2 right there, you'd know we were using base 10. Now, if a to the b is equal to c, then b is equal to the log base a of c. This a here is a little bit out of place. Sorry about that. This a here is a little bit out of place. If a to the b is equal to c, then b is equal to log base a of c. And if b is equal to log base a of c, then the a to the b is equal to c. This is probably the number one important rule. The log base, now another rule is the log base a of 1 will always equal 0. Another one, as mentioned in a previous, and that's because a to the 0 will equal 1. Another important rule is the log base a of a to the x is equal to x. We really relied on that rule when we were establishing why the three main rules of logarithms work. Another rule we mentioned a while ago in a previous video is that a to the log base a of x will equal x. Now, here's our product rule of logarithms. The log base a of mn is log base a of m plus log base a of n. The log base a of m over n is log base a of m minus log base a of n. The power rule, the log base a of m to the n equals n log base a of m. And then our two change of base rules that we just learned. Let's put some of these to use. Let's evaluate the log base 5 of 343 over the log base 5 of 49 and show that we didn't need a calculator. Well, looking at this, I say to myself, gosh, I don't know what the log base 5 of 343 is, and I don't know what the log base 5 of 49 is. We're really in trouble. But then I have number sense, and I remember that 343 is equal to 7 cubed. And 49 is equal to 7 squared. So why don't I just change this 5 and this 5, since they're both the same? Why don't I change them each to a 7? Okay, so instead of saying log base 5 of 343 over log base 5 of 49, let's say log base 7 of 343 over log base 7 of 49. If you go back a slide previous, this is literally the last rule shown on the page. And so we're going to use it to our advantage right now. So the log base 7 of 343 is 3 because 7 to the 3 is 343. The log base 7 of 49 is 2 because 7 to the 2 is 49. And so our final answer is 3 over 2. Now let's solve this equation. 5 to the 3x plus 1 equals 14 to the 2x minus 3. And we're going to round our answer to 2 decimal places. Okay, well, we don't have similar bases. We can't make the bases the same. It's not like one of them's a 3 and the other's a 9. There's no real relationship between 5 and 14 that's going to help us there. So what are we going to do? Well, when you can't solve an equation by making each exponent have the same base, take the log of each side. Now, it might not be obvious at first why we're doing this, but check this out. It's really neat. We're going to take the log of this expression and the log of this expression. Now, we can take this exponent and bring it in front, and we can take this exponent and bring it in front. And so we've got is 3x plus 1 quantity times log 5 equals 2x minus 3 quantity log 14. Next, what we can do is distribute. So this log of 5 is going to multiply by 3x, and it's going to multiply by 1. And this log 14 will multiply by 2x and by negative 3. And so what we get is 3x log 5 plus log 5 equals 2x log 14 minus 3 log 14. Now, we want to isolate x ultimately, so we get our x terms on one side, and we get our other terms on the other side. So we bring this over here, bring that over here, so to speak. Okay, and that's what we get in this line right here. Now, we've got two terms each with x, so we can factor x out. X times 3 log 5 minus 2 log 14 equals negative 3 log 14 minus log 5. Now we can divide each side by the coefficient of x. And the coefficient of x here is 3 log 5 minus 2 log 14. And so that's what we get here. And if we want to evaluate the numerator, it's roughly negative 4.137354. And evaluating the denominator, it's roughly negative 0.195346. And so the ultimately, x is roughly equal to 21.18. And so basically what we're saying is that 3x plus 1 would be equal to roughly 64.54. And 2x minus 3 would be equal to roughly 39.36. So basically what we're saying is that these two values are roughly equal to each other. Okay? Now, this is fine if we're just asked to round the answer to 2 decimal places. But maybe the question's a little more sophisticated. If we're asking for an exact value, we can give that value that you see right there. That's a precise value. Of course, it's approximately 21.18, but it's an exact value. But if we're asked to round to 2 decimal places, we could give that value down at the bottom. Now, you might be asked, though, in an even more sophisticated question to give your answer as 1 logarithm. As we said a minute ago, this is the exact value, but it's not expressed as 1 logarithm. Let's express that circled value as 1 logarithm. Okay? So we have the circled value showing up again right here. Now, since both of the terms in the numerator are negative and one of the terms in the denominator is negative, let's start by doing something really simple. Multiply numerator and denominator both by negative 1. That'll, instead of having 3 out of 4 terms negative, we'll have 3 out of 4 terms positive. So we'll have 3 log 14 plus log of 5 over negative 3 log of 5 plus 2 log of 14. And then, as you might imagine, it's more typical to write 3 log of 14 plus log of 5 and to write the denominator as probably 2 log of 14 minus 3 log of 5. Okay, so let's say that we state our expression like that. Okay, and this is what we've just shown. Now, what we can do is use the power law of logarithms, and we can bring this 3 up to become the exponent on the 14, and then bring this 2 up to become the exponent on the 14, and this 3 up to become the exponent on the 5. When we do that, And this is what we get. Okay? Now, 14 cubed is equal to 2,744. 14 squared is equal to 196, and 5 cubed is equal to 125. So we can re-express everything this way. Now, look at what's up top. We've got the log of 2744 plus the log of 5. Why don't we make that the log of 2744 times 5? And we've got the log of 196 minus the log of 125. Why don't we make that the log of 196 over 125? So up top, we'll have this. And down below, we'll have this. Okay? So, we end up with the log of 13,720 divided by the log of 196 over 125. Now, go back a little while ago to what we said at the start of this slideshow. We said that since 2 cubed is equal to 8, therefore 3 is equal to the log of 8 over the log of 2. But we could have written that instead as log base 2 of 8. In other words, when we have an expression written like this, we can write it like this instead. Well, why don't we do that right now? We have an expression written like this, which is basically this form right here. Why don't we write it in this form? So what that's going to be is the log base 196 over 125 of 13,720. And this is what we get. Okay? And so I believe we said a while ago that the answer to that was roughly 21.18. We said earlier that that answer was roughly 21.18. But in fact, stating it the most sophisticated way possible, what it really is this expression right here. And if you're wondering, does 21.18 equal the log base 196 over 125 of 13,720? The answer is yes. And the reason being, because 196 over 195 to the exponent 21.18 is roughly equal to 13,720. Okay, moving on. Word problem question. A population of bacteria doubles in population every day. How many days will it take for a population of 20 bacteria to increase to 55,000? All right, well, we can use the formula A equals P times B to the N, where the initial amount is 20 and the final amount is 55,000. The multiplier is 2 because we're doubling every day, so n will be the number of times that multiplier is used, in other words, the number of days. And so what we get when we plug those numbers in, we get this expression right here. When we divide both sides by 20, we get this expression. 55,000 over 20 is 2,750. And so what we get is 2,750 equals 2 to the n, or in other words, n equals log base 2 of 2,750, which is approximately 11.4. If your calculator has a log base 2 button, you can do just like it's shown in that line. If it doesn't, then you can say either n equals the log of 2750 over the log of 2, or if you want to use the ln button, you can say ln of 2750 over the ln of 2. So long as you're using the same button in the numerator and denominator in that situation. Either way, it's roughly 11.4. It'll take roughly 11.4 days to grow to 55,000 bacteria. Now, suppose there were 90,000 grams of a particular radioactive substance 8 hours ago, but now there are only 250 grams. We want to know the length of one half-life rounded to the nearest minute. Okay, well, a half-life is the length of time it takes for a substance to decay to 1/2 of its original amount. So what we're using here is a base of 1/2. not 2. We can say A is equal to 250 because that's the final amount, and the initial amount is 90,000. And we know that N is unknown at the present time. So 250 equals 90,000. There's an extra 0 here by accident. 90,000 times 1/2 to the exponent N. So what we can do is divide both sides by 90,000, and we've got 250 over 90,000 equaling 1/2 to the exponent N. So N is the log base 1/2 of 250 over 90,000. If we want to express that as the log of 250 over 90,000 over the log of 1/2, we can. But however it is that we simplify that, the answer is roughly 8.49185. Okay? What that means is that in 8 hours, we have lived through approximately 8.49185 half-lives. Because if you go back to this expression here, 1/2 to the n, when 1/2 is the multiplier, n is the number of half-lives, because n is the number of times we've multiplied by 1/2. That's the number of half-lives. So 8.49185 half-lives is occurring every 8 hours. Okay, so 8 hours is roughly 8.49185 half-lives. So 8 hours divided by that number is going to equal roughly 1 half-life. Well, 8 hours is equal to 480 minutes. So 480 minutes divided by 8.49185 is approximately 57. And so 57 minutes is the approximate length of 1 half-life in that situation.